Hello, and welcome to Physics for Play. In this episode, we're going to be talking about mode coupling, and we're also going to be talking about the Fermi pasta Ulam Tsingou problem. Let's get started. Today is going to be kind of a special topic. We're going to be talking a bit about mode coupling and the Fput problem. So we're going to go into a little bit of review on linear superposition. We're going to talk about how does a system thermalize. We haven't really talked about any sort of thermal physics, but we'll give you some background there. And then we'll go into a kind of a classic simulation of the Fput problem. So to start, you may recall that if you've ever seen a rainbow or a prism before, you may recall that white light is made of all the colors in the rainbow, and the way that a prism works is that it separates those individual colors. So the colors in the rainbow are monochromatic, which means they only have a single frequency of light. So for example, red light is around 700 nanometers of wavelength, and there's a corresponding frequency to that. But it's a very particular frequency. Similarly, music and speech are made of many superposed pure tones that correspond to a single pitch or frequency of sound. So while white light and music and sound may have very complicated oscillatory patterns, they're all made of a superposition of single sinusoidal motions. When we have a prism, that's a tool that can separate white light into its various monochromatic components. And there's a mathematical version of a prism, which is called Fourier analysis, which can decompose a function into sums of simpler sinusoidal functions. We could do a whole video series, to be frank, of Fourier analysis and the different things that you can do with it. We're going to touch on it a little bit today, but we're not going to go into any depth of it. We might do that in a later video. But what we really want to do is look at how can we decompose the motion of an oscillator into, or a system of oscillators, into its normal modes, into a linear superposition of normal modes. And there's kind of a classic, historically interesting, at least for physicists, problem called the Fput problem, related to how systems, when they get heated up, how they thermalize. How do they transfer energy between different oscillatory modes? So here's what we know about physical systems. At thermal equilibrium, a system has energy distributed throughout all of its modes of vibration, and the amount of energy it gets is given by a distribution function that is related to the energy. We won't go into massive amounts of detail on that. But we will say that normal modes of linear systems can be superposed, and they do not interact with each other. If we are in a linear system, the normal modes of that system will not interact with each other. And that means that those normal modes can't pass energy back and forth between them. So if a linear system starts in a specific mode, it will remain in that mode forever. For the entire lifetime of that mode. So then the question is, if you're heating up a system, or you have a system that's been heated up, and you leave it alone for a long time, well, how does the energy get passed back and forth between the different modes of vibration? Because the energy is distributed through all the different modes if the system's at thermal equilibrium. How can that happen if a linear system won't allow you to do that because you can't pass energy between the modes? And this was a question that Fermi, Pasta, Ulam, and Tsingou looked at. This was in a 1950 paper. It was one of the first computational problems solved with physics. It's a paper called Studies of Nonlinear Problems. If you look it up online, you can find a copy of it. In the abstract, they talk about a one-dimensional dynamic system of 64 particles that they used, that they simulated in Los Alamos National Lab using the computer Maniac 1, which is one of the first supercomputers. Your flip phone of 10 years ago probably had more computing power than it, but for the time, this was quite an impressive feat. And what they did, since they knew a linear system could not solve the thermalization problem, they created a nonlinear system that they did a numerical simulation of, and it included, they did a few different nonlinear simulations, and it included a force that had a quadratic term in it, so not just the linear force. And we're going to reproduce that today. But before we do, we are going to start. We're going to start with just the linear case. So we're going to go ahead. We're going to set up our equations. We're going to solve those equations. We'll animate the solution, and then we're going to compute the power spectrum of the system. So the power spectrum is basically a fancy way of saying we're going to figure out how much energy is in each of the normal modes of the system. So we're going to start simple. We're going to keep the number of particles small, just to get things set up, and then we'll bump it up to 32. We're going to start with 4 particles. We're going to keep the mass. This should be the no, I'm sorry, this is not the mass. This is the mode number. We're going to start in the lowest mode. We're going to start in the first mode. We're going to start with no nonlinear term. So the way Fermi, Pasta, Ulam, and Tsingou set their system up, they had a linear term of oscillators that were all coupled together. And they had a nonlinear term that had a factor alpha in front. So if alpha is 0, then that term is no longer there. So we're going to start just with a linear system. And we're going to set some amplitude, which I've called Cm here, for the nth mode. I will hold here, so if anybody wants to pause the video and copy these down, you can. One bit of code which I have not showed you is that we are using subscripts here. So if you notice the symbol here, x sub I, you can just use the subscript command and then copy that from there to get your equations and motions. Because all we're going to have is we're going to have n coupled oscillators. In this case, n is 4, and we're going to make a table of the equations of motion. And the equations of motion, we're just copying down this equation of motion. So we've got, this is very similar to the 2 coupled masses problem, except we're going to have more masses. So we've got the linear term, we've got the nonlinear term, and this will give us our equation of motion. We will set up our initial condition. The initial condition, we're going to put the system in the first mode of the system. So we're just going to make the masses arranged in a little sine wave where they're going to be oscillating up and down. It'll be a little bit different than the example we gave before, because these masses will be oscillating up and down vertically, like you would see on like a guitar string that's been plucked. So we'll set our equations of motion up, we'll set our initial conditions up, and then we'll set our boundary conditions up. And we're going to have particles going from an index of 1 to n, but we are going to include x equals 0. We're just going to say that that's going to be where the wall is. We're going to fix the boundary condition there so that position is always going to be 0. And similarly, we're going to define a position x sub n plus 1. That'll be the other boundary. That'll be another wall that the masses are attached to via a spring. That also is not going to be going anywhere. So we have fixed boundary conditions on either side, and then masses connected in a series via springs in the middle. So we're just going to run this. We're going to solve our equations of motion using ND-solve. The numerical differential equation solver will do it for a total time of 30,000 units. And we will animate that solution. So you can see this is the, that's going faster than I would like it to. You can see our initial position just kind of looks like a sine wave, nothing too complicated. And when I set it in motion, you can see it just oscillates up and down. Again, it's like you plucked a guitar string, and these are the different atoms in the string, or the different mass components on the string. So we've animated the solution. Now, we put it in the first mode, and you can see as I animate this, it pretty much just stays in the first mode. It just looks like a sine function. We'll make it a little bit more complicated momentarily. But let's compute the power spectrum of that oscillation. I put a reference here that goes into more detail on how to compute this. So I'm not going to do a full proof of where the power spectrum is going to come from. I'll just show you this reference. And we'll do an example with the 4 masses. So what we're going to do is we're going to compute, so between each mass I minus 1 and mass I, there is a spring. And the stretching of the spring is given by xi minus 1 minus xi. So I'm setting most of my constants, my spring constants here, all equal to 1, so I don't have to worry about them. But the spring energy, if we set the stiffness equal to 1, will be 1/2 the difference between those two adjacent mass positions squared. And I'm going to replace these times with times t equals 0. So that's the standard way of computing the spring potential energy. Now, again, I'm not going to go through the math of proving this, but there is a thing you can do called a Fourier transform. If you want the equation for it, you can look it up here. You can also look up tons of YouTube videos on the Fourier transform. But we are going to use Fourier transform and Parseval's theorem to compute what the energy would be in terms of these Fourier components. So these Fourier components tell me how much of each normal mode the system has. So if I start with a system like this, it should tell me that the system only has energy in the first mode because that's the mode that the system's in. So we're going to go ahead and run this. And all I'm doing here is just showing you that if you compute the potential energy the standard way, and if you compute it after doing a Fourier transform and using Parseval's theorem, you get the same result. We can do the same thing for the kinetic energy. Again, we'll compute it using the standard formula for kinetic energy, which is 1/2 mv squared. And then we're going to Fourier transform that system. When you're doing the Fourier transform, you're transforming from the displacements to the Fourier components, which get written as a sub k. Or equivalently, if you're Fourier transforming the velocity, you transform the velocity components. Again, I'm not going to go through the math here. I'm just going to show you that, hey, look, you get the same kinetic energy if you use Parseval's theorem and do the Fourier transform. Feel free to look up what Parseval's theorem is. Feel free to look up what a Fourier transform is. But that's all I'm going to say about computing those modes. We are just going to figure out which of the modes we want to compute. In this case, we're going to compute how much energy is in the first 5 modes. We're going to compute the potential energy, the kinetic energy. We're going to add those two together to get the total energy. And then we're going to list plot how much energy each mode gets as a function of time. So how much energy is in the first mode? How much energy is in the second mode? How much energy is in the third mode? And we'll make a plot of that. So we'll run that. And you can see, as we should, the first mode gets all the energy. Everything else is at 0. No other energy is showing up. We can just verify that this is actually what's happening. I'm going to change the mode number here. Again, this is the mode number, not the mass. I'll put it in the second mode. I'll solve the system of equations. We'll animate it and show that it is, in fact, slow that down a bit. You can see you are in the second mode. It's hard to see that this is a sine wave given that there's so few points, but you can see that it's going up and down. And if we compute the power spectrum, you'll see, this will just take a second. You'll see now all of the energy is in that second mode, the orange line, whereas the first mode, the blue, the third mode, the green, the red mode, the blue, the fourth mode, the red one, and the fifth one, the purple, they're all at 0. So seemingly, we can not only compute the energy, but we can figure out how much energy is in each mode. So I'm going to go back up here. I am going to put us back in the first mode. And I'm going to give us more particles to play with. So just like Fermi, Pasta, and Ulam, we're going to simulate this with, well, I guess I'm going to leave it as, well, we'll do 64. We'll live dangerously. The only reason not to do 64 is that it might, it's going to slow the simulation up. Well, I'll do 32. We'll keep it a little bit faster. We'll set our system of equations up. We'll run our ND solve. We will now, system's already updated, so it's now animating those 32 modes. I'm going to speed it up a bit. You can see it's just staying in that first mode. If I jump to the second mode, again, solve the system of differential equations, you can see we start now in the second mode, and you can see it oscillates at a higher frequency in that second mode. If I compute the power spectrum for this, since we just computed it in the second mode, we should again have all of the energy being in that second mode, which we do. We'll do it one more time, just for completeness sake. We'll put our system in the third mode, solve the differential equation, animate the solution, slow it down because it's way too fast, and you can see we're in the third mode of oscillation. And if we compute the energy per mode, you will see, give it a second, you'll see now all of the energy is in the third mode, which is green. Now, we could have, I'm not going to do this here. If you want to play around, you could put this in a superposition of modes to start off with. And then when you compute the energy in the mode, you would see, say you put 2/3 of the energy in the first mode and 1/3 of the energy in the second mode, you'd see a blue line up here, and then a little ways down here, you would see the yellow line showing you how much energy each mode gets. We're not going to do that. We're going to keep our system, we're going to put our system in the first mode, but we're going to put in a nonlinear term. Now, Fermi's hypothesis was that when you include nonlinear forces in here, all of a sudden, everything we said about linear systems, that the modes don't interact with each other, they can't exchange energy. Well, that should be changed here. Now they can interact, they can exchange energy. So maybe this is what we need to thermalize the system so that each mode gets a certain amount of energy and then it stays with that amount of energy. That was the hypothesis that Fermi Pasta, Ulam, and Tsingou had. And we're going to try that now. So we'll run that. We'll solve our system of equations. We will animate the solution. And already you can see something interesting is happening here. So it's not just staying sinusoidal. You can see it's starting to, it's starting to whip around in, the maximum peak is starting to whip around almost like it's going in a circle. And now it's doing it a lot. And now I don't look like I'm in the first mode at all. We'll let that run for a second or so. You can see, looks like there's some waves going back and forth. Now it's looking like I'm closer to being in the third mode. We're letting that run for a while. Now it really is looking like the third mode. And we'll speed this up a little bit. Whoa, what's that? It looks like it's in the second mode. And come on, you can do it. Go back. I'm going to cheat. I'm going to move us ahead a little bit. Fast forward the animation. You can see it's starting to look like it's back in the first mode. Look at that. There's a point in here where it looks like it's kind of back to almost mode number 1 again, where you had just that single hump in the sine function. What's up with that? Well, let's compute the power spectrum and see what the energy in each mode looks like. This will just take a second. So it definitely did not all stay in the first mode. Let's see what it actually looks like. Now I'm not just getting straight lines where the energy stays all in one mode. But it's not just a constant energy that's getting distributed throughout the modes. There is some quasi-periodic pattern here. You see, we start with the energy in the first mode. That's the one hump. And the energy starts getting sapped from that mode. You can see the other modes start picking up energy. The second mode picks up energy. The third and fourth modes start picking up some energy. But then those modes start losing energy, and the first mode starts picking up more energy. And it's this sort of, it's not quite periodic because it doesn't go all the way to the top. But you can see pretty much the same thing that Fermi and Fermi Pasta and Ulam saw, which was surprising, which is that it wasn't just that the energy leaked into the other modes and then the system thermalized and then the energy stayed roughly constant, which you would expect for thermal equilibrium, roughly constant within each mode. You could start to see that there was some more rich behavior of physics going on here. So I won't go into all the detail on this. You are more than welcome to read the Fermi Pasta Ulam and Tsingou paper to go into the detail here. But the point is that you are now set up to solve physics problems that you can't do with pen and paper. Physics problems that if you tweak some parameters with, you can actually find some real research, do some real research and make hypotheses, try to experiment and figure out how the physics works. So I am going to stop here. before the video gets too long. Thank you so much for watching. If you like the video, please click like, and if you'd like to see more, please click subscribe.